people. Okay, day 2 of number theory. We're going to start off. Okay, so we're going to start off with the homework review from yesterday. And then we're going to cover some rules to find the number of factors of a number. And we're also going to go over product of factors, plus some AMC 8 problems. All right, so this was the first problem on the homework. Find the prime factorization of 20,551,388. So if you solve this or want to take a guess at it, you can put your answer in the chat. Yep, that would be the correct answer. So as you can see here, this is a factor tree, and then it helps us find the prime factorization more easily. So we just break it down into component factors. Like see here, we pull out a 2 squared, and then divide that by 4. That gets you this. You pull out an 11, and then you just continue down until all of the numbers that you have are primes. And then you write them over here in this format. So 2 squared times 11 times 13 times 19 times 31 times 61 is the prime factorization of this number. All right, good job. What is the value of the least common multiple divided by the greatest common factor of 90,751,469 and 171,593? So again, you can put your answers in the chat. Yeah, this one is definitely tricky. The numbers are kind of outrageously large. But so here, as always, the first step is to find the prime factorizations of both numbers. And as we went over yesterday, you can use that prime factorization to find both the greatest common factor and the least common multiple. So the greatest common factor would be whichever factors are shared between both of the prime factorizations. So you can see that both of them have a 29 and both of them have a 61. So those multiplied together become the greatest common factor. And then LCM is basically you look at each distinct prime number and then look at the highest exponent that's present. So for example, there's a 29 in one of the numbers and then there's a 29 cubed in the other number. So we take the 29 cubed because that's the larger exponent. And so we do that for all the numbers. So we take the 61 squared instead of the 61, and then we take 97. So multiply those together and that becomes the least common multiple. Then the question asks us for the value of the LCM divided by the GCF. So you can see like our equation down there at the bottom. And so the answer to this problem is 4,976,197. But this problem is a bit weird because the numbers are just like kind of ridiculously large. So don't worry too much about it. And also, before we move on, how confident do you guys feel about prime factorization? Because we're going to be using that like basically throughout the whole lesson, and you guys need to be very familiar with it. You can like rate it from 1 to 5 in the chat if you want, or even private message me. just send me a number, 1 through 5, 5 being like, I've got this all completely down, and 1 being like, I have no idea what prime factorization is. The answer to this problem is 4,976,197. You can see it at the bottom of the screen. All right, no one has said that they're very confused about prime factorization. So let's continue then. In a band, musicians are expected to stay in a rectangular formation of rows and columns. When musicians are in rows of rows of 6, 2 people are left out. When the musicians are in rows of 8, 9, and 11, 2 people are also left out. What is the least number of people in the band? So how'd you guys do on this one? Yeah, sure. All right, so did anyone get the answer for number 3? Okay, well, I'll go ahead and explain it. So I hope it's fine to move on, Aditya. So basically this question, we had a couple of examples similar to this yesterday. So basically, 2 people are left out no matter whether they put in rows of 6, 8, 9, and 11. And so an easy way to find what number that is to just find the least common multiple of 6, 8, 9, and 11. So that's where like everyone can be put in even rows with no one left over, and they can be like in any of those numbers of rows. Then you just add 2 because those are the 2 people that are left out. So we find the least common multiple of that, which is 792. And then we add 2 to that to get 794 musicians as the least possible number of people. Okay. Also, if you guys have any questions at any moment, just feel free to type it in the chat. Okay, problem 4. I have a cabinet of CDs, and if I stack as many as I can in 9 stacks, there are 4 remaining CDs. And if I stack as many as I can in 13 stacks, there are 8 remaining CDs. If I stack as many CDs as I can in 17 stacks, there are 12 CDs remaining. So what is the least amount of CDs I can have? This is similar to the other one, but maybe a little bit harder to see the pattern. So when solving this one, we would go, we would find the least common multiple of 9, 13, and 17, like we did before. But also we have to add or subtract a number because, you know, there's not an even amount in each stack. So does anyone, if you have a guess at what number we should subtract or add, type it in the chat based on like the number of remaining CDs. Can you notice a pattern in it? Nobody? Okay, so the pattern here is that the number of CDs remaining is always 5 less than the number of stacks. So you find the LCM of 9, 13, and 17, and then you subtract 5 from that. So that would be 1,989 minus 5, which is 1,984 CDs. All right, then final problem, 5th problem. This is basically the same concept as the other two, but this one's like even harder. You have to do more steps. So I think I can go ahead and explain this one. So here, so basically the first line and then the third line, that tells you that you can find the least common multiple of 9 and 15, and then add 7 to that. Then the amount of books is like some multiple of that. Okay, it could be like 2 times that, but you're looking for the least amount of books. So you're looking to minimize it. And then the second line of the question tells you that the amount of books is also like 9 plus a multiple of 11. So the least common multiple of 9 and 15 is 45. And then if you subtract 9 from that, you get 36, but that's not a multiple of 11, so it doesn't fit the second criteria. So then we try upping it by another multiple. So 45 times 2. Yeah, this slideshow will go into Google Classroom and the recording. So you add 7 to that, and then you get 97. And then you subtract 9 to see if it meets that multiple of 11 criteria, which it does, because 88 is a multiple of 11. And so that means that the minimum possible number of books is 97. So sometimes you just have to do trial and error to find their answer, especially for those like least possible amount. Okay, so now we're going to move on to finding the number of factors using prime factorization. So first, we're going to practice manually calculating how many factors a number may have. So I want you guys to try to find the number of factors that 24 has. You might have learned something called the factor rainbow in elementary school, so you can use that and then just type in chat when you get your answer. Yeah, just say how many factors 24 has. All right, so we seem split between 6 and 8. The answer here is actually 8 factors. So it's easy to miss some. So there would be 1 and 24, 2 and 12, 3 and 8, and then 4 and 6. Those are the 8 factors, 24. So how does this relate to prime factorization? Well, how do you find the factors of a number? So when you're finding the factors of a number, you're supposed to be multiplying some combination of the prime factors together. 24's prime factorization is 2 cubed times 3. And that means that all the factors of 24, the 8 factors we just found, are some product of either 2 to the 0th, 2 to the 1st, to the 2 cubed, or 2 squared, multiplied by 3 to the 0th power, or 3 to the 1st power. And just as a side note, anything raised to the power of 0, anything with that exponent of 0 is equal to 1. So that might have been somewhat confusing, but I'll explain. So say let's take 12. 12 would be 2 squared times 3 to the 1st power. Or let's take 4, another one of the factors we found, that would just be 2 squared multiplied by 3 to the 0th power. So all the factors of 24 are just some combination of its prime factorization. And now there are 4 possible ways to have an exponent from 2 to the 0th to 2 to the 3rd. And then there's 2 ways to have an exponent between 3 to the 0th or 3 to the 1st power. So we're trying to find how many combinations there are. This is something you'll learn more in counting and probability if you take that. But basically we multiply the possibilities to get 4 times 2. And so we're going to break that down further in a diagram here. So you can see basically we have a line from 2 to the 0th to 3 to the 0th, 2 to the 0th to 3 to the 1st, all of those lines. And that goes into how many factors. There are 8 lines total. But then we noticed another pattern. So you see, so basically a simple rule for this is to look at the prime factorization. Here that's 2 cubed times 3. And then you look at the exponents of that prime factorization. So here, that would be this 3 here, and then this hidden 1, because we don't have to write that when it's only 1. Then you take that over here, and you add 1 to each of those exponents. So 3 plus 1 is 4, 1 plus 1 is 2. 4 times 2, and then you multiply those together to get 8 factors. So basically, find the prime factorization, then take out the exponents, add 1 to each of the exponents, then multiply them together. And that works because of like this diagram below and what we explained earlier about how all the factors are a combination of the prime factors. Okay. Does anyone want me to go back over something I just said? All right. So basically, this is an easy rule to calculate the total number of factors a number has very quickly. And again, add 1 to the exponents in the prime factorization and then multiply those exponents together. So we're going to try some examples. And this method works the best on bigger numbers. So I want you guys to try out finding the number of factors that 70,000 has. And it's okay if you don't get it, because we're going to go over it, and hopefully doing it step by step will help make more sense. I'll give you guys a minute or two to try. Okay, so starting off, has anyone found the prime factorization of 70,000 yet? Okay, that's the first step. So if you have found it, type it in the chat. Yeah, sure. 2 more. All right, that's very close. The answer is actually 50 factors. So let's just go through the process and maybe you'll see. Oh, okay. Oh wait, were you like counting them manually? Oh, okay, well, let's use the method that we're learning, okay? So first, find the prime factorization of the number. That's the prime factorization. Second step, take the exponents. So the exponents of that prime factorization are 4, 2 to the 4th, 5 to the 4th, 7 to the 1st power. So the exponents are 4, 4, and 1. Now you just add 1 to each of those exponents. So it becomes 5, 5, and 2. And then you multiply those exponents together. 5 times 5 times 2 equals 50. So that's the easy way to do it. You can manually find it like this, but that looks like a huge pain. So I wouldn't recommend that. And so that gets you 50 factors, okay? So you guys should be using the faster method to do it. All right. What is the number of factors of 1776? Go ahead and try this one out. Right. In fact, we can go ahead and prime factor it together to make it a bit easier. So 1776, that can be divisible by 2. So let's see, what is 1776 divided by 2? That would be 888. Divided by 2, that would be 444. 222. Take out another 2. And now we have 111, which is 3 times 37. And that's our prime factorization. 2 to the 4th times 3 to the 1st times 37 to the 1st. Sorry, that's really bad. 37 to the 1st. So now you should be able to use the rule to find the number of factors from there. Right. Jivitesh is correct. The answer is 20. Akshat, are you using the rule or are you just counting them again? Because it is really easy to miss things when you're counting. Okay, so remember the rule. Let's see here. So we factored that correctly. And then now we find the exponents, which are 4, 1, and 1. Then we add 1 to each of those exponents, getting 5, 2, and 2. Then we multiply those together to get 20. 5 times 2 times 2 equals 20. Okay. So we have a few more examples just for practice. 1,834. All right. Here's the prime factorization up there, just to make it easy, okay? And then all you have to do is apply the rule. Yeah, 8 factors is correct here. So the exponents are 1, 1, and 1. So if we add 1 to all of them, then we get 2, 2, 2. Then all we have to do is multiply those together. And so 1,834 has 8 factors. Okay, another example. And here's the prime factorization. All right, I won't give you guys the prime factorization for all of them, but just for a few here. All right, it looks like you guys have the hang of it mostly. So the exponents are 2, 1, and 1. Add 1 to all of them, they become 3, 2, 2. And then you multiply those together to get 12. So good job. Those of you who put 12 in the chat. All right, now for 3,600. So this one is relatively easy to prime factorize. So I want you guys to try to do that bit on your own. And then find the number of factors. Okay, you are correct if you said 45. So the prime factorization of 3,600 is 2 to the 4th times 3 squared times 5 squared. And then the exponents are 4, 2, and 2. If you add 1 to them, that becomes 5, 3, and 3. And 5 times 3 times 3 equals 45. So good job. All right, next one. 7,623. All right, I think I can just go ahead and get the prime factorization because we're trying to mostly practice applying this rule. Yep, great. Exponents are 2, 1, and 2. If you add 1 to them, you get 3, 2, and 3. And then multiply together, that gets 18. Okay, we have a lot of examples here just to like really pound it into your heads. Okay. Yep, 12 is correct. 3 times 2 times 2. All right. So I want you guys to try actually finding the prime factorization of this one then. Yep, the answer is 48. So that's the prime factorization up there. And if you find the exponents, then add 1 to all of them, then multiply that together, you get 48. Okay, just a couple more. What is the number of factors of 43,575? Yeah, 24 factors. So find the exponents, add 1, multiply. 24 factors. Okay. Number of factors of 192,780. Here's the prime factorization. That's all right. Just check your work. Maybe both of you. Yeah, so this one is 120 factors. So the exponents are 2, 4, 1, 1, and 1. So you add 1 to all of those, and then you multiply them all together. All right, we're just gonna do this last one and then move on. Okay, wait, we're gonna skip this one. This one's strange. Okay, this one is a good example of one I think you guys can find the prime factorization of on your own pretty easily. So go ahead and try it. You're close, but not quite. It's easy to mess up on really larger numbers like these though. So I'll just go ahead and we can find the prime factorization. It is also not 120, but both of you are close. So 864,000. We divide that into 1,000. Lots of ways to do this, but this is just how I would do it. And then And each of these go into 2 and 5. Okay, and then now we break down 864. So we take out 2 because it's even, so we know we can take out a 2 and get 432 to 216. Take out another 2, 108 to 54 to 27, 9, 3, 3, and 3. So that's how you break it down. And now if we count them up, we should have 8 2s. 2 to the 8th power times how many 3s? Oh, maybe you guys are right. I think the answer on this slide might be wrong. Okay, so 3 to the 3rd, and then how many 5s? 1, 2, 3, 3 5s. So then 9 times 4 times 4 would be 144. Okay, so you guys are right. Sorry about that. But good job. I think there's just a small mistake on the slides. Yeah. Okay. Ignore that. All right, so let's just move on. We're going to skip past this one and onto the number of factors, but we're trying to find the multiple of something. So sometimes there will be problems concerning like how many factors a number has, but it concerns how many factors are a multiple of some number. So for example, how many factors of 58,480 are even? Or basically, how many of them are multiples of 2? Well, again, we have to find the prime factorization like this. And for a number to be even, it must have a 2 in its prime factorization. So okay, so we're going to see this diagram. And then, okay, so listen closely. So this one on the left is the correct diagram for this problem, oops, because and basically all we're doing is taking out 4 to the 0, 2 to the 0th power, because if something 2 to the 0th power is just 1, and then that if something has 2 to the 0th power, it's not an even number. It has to have a higher power of 2, because if it because otherwise it's just not going to be even. So our equation is a little bit different because now we don't add 1 to our exponent for 2, we just leave it the same. So our exponent for 2 is 4, and we just leave it as 4 in our equation, but we still do plus 1 to all of the other exponents. So our final equation is 4 times 2 times 2 times 2, and that gets us 32 even factors. Okay, so we're going to try 2 problems using that same principle. How many factors of 68,607 are divisible by 9? And how many factors of 32,674 are odd? So you can try this, go ahead and try this on your own. Small hint, 9 is just like 3 squared. So it must have at least like 3 to the 2nd power in it. And then the even one is the same as what we just did. It can't, you have to take out 2 to the 0th power as an option. So you have 5 minutes to try this. All right, so maybe this is stumping you, but it is pretty challenging. So we can go ahead and explain again. So let's see, let's take the first one. How many factors of 68,607 are divisible by 9? So first step, always find the prime factorization. And second step, we kind of have to extrapolate this from the question. So a number that is divisible by 9 has 3 to the x as a factor, where x is an integer greater than or equal to 2. So basically, if something has 3 squared as a factor, or 3 cubed as a factor, or 3 to the 4th as a factor, then it will be divisible by 9. So basically, we're just seeing how many of its factors fall into that criteria of being like 3 to the x, where x is greater than 2. So our equation, okay, maybe ignore that for now. So basically, if we were doing our equation as normal, we would just add 1 to the exponents, and then we get 5 times 2 times 3, right? But now not all of the multiples of 3 fit into our criteria. So we have to see which ones do. So 3 to the 0th power, that doesn't work because it's smaller than 2. 3 to the 1st power also doesn't work because it's smaller than 2. But all of the other ones do work. So instead of writing like a 5 here into our equation, we subtract 2 from that, the 2 options that don't work, and we only have a 3. The others remain the same because we don't care about them in this question, really. So here's another explanation. So like 3 squared, 3 cubed, and 3 to the 4th fit the criteria. And so our answer here is 18 factors. Does that kind of make sense? And can you see why that's the case? Okay, so the other question is a bit simpler than that one. It is how many factors of 32,674 are odd? So first, prime factorization as always. And so for a number to be odd, it cannot have like any 2 in its prime factorization. So our equation is 1 times 2 times 3. The 1 is just for like 2 to the 0th power, because that equals 1, and that doesn't put a 2 in the prime factorization. And then for like the exponent over 17 and the exponent over 32, we just do like 1 plus the exponent like normal. 2 is the special one here because we're trying to find only the odd ones, and so it cannot have a 2. It cannot have 2 to the 1st power in there. So then our answer is 6 factors here. What you could have also done is find the total number of factors like normal, and then just subtract the number of even factors, which we saw how to do in the first example. But hopefully that lesson doesn't confuse you. It's just another way of doing it. And then, okay, so there can also be problems concerning how many of the factors are squares or cubes. So for example, how many factors of 21,600 are squares? So first we find prime factorization of that. And so for a number to be square, the exponents of all the values in its prime factorization have to be even. And so basically we're going to look for those exponents. We're going to find how many of them can be even. So 2 to the 0th, 2 to the square, 2 squared, and 2 to the 4th power, those are three options that are going to be even. And then 3 to the 0th and 3 to the 2nd are two options that are going to be even. 5 to the 0th and 5 to the 2nd are two options that are going to be even from the prime factorization of 21,600. And so the number of combinations from only those even exponents is 3 times 2 times 2. So then that tells us that there are 12 factors here that are perfect squares. Okay, so we can try out these problems. How many factors of that number aren't perfect squares, and how many of its factors are perfect cubes? Okay. So I think it's probably best if we just walk through these step by step. So how many factors of it are perfect squares? Well, okay, type in the chat, what's always the first step when we're solving problems like these? The absolute first step, which I've repeated a bunch of times. Okay, or maybe what's the first step you would do? Yeah, perfect. Find the prime factorization. So it's up there now. And for something to be, so what we're going to do here is to find a strategy of finding all the total factors and subtracting how many perfect squares there are to find how many aren't perfect squares. So for a number to be a perfect square, you have to have even exponents for all numbers. And so that's how many perfect squares there are. So here's how exactly it gets calculated. So we're finding the number of perfect squares, and then we look for only the even exponents for all the numbers. So taking this prime factorization, like 2 to the 6th is the maximum. You can go 3 to the 4th, 5 to the 2nd, and you find how many even exponents there are that are smaller or equal to the prime factorization, if that makes sense. And then you just multiply them as normal, multiply the possibilities, and that tells you how many total possibilities there are. And so then you go back and do it normally. So where you just find the exponents 6, 4, and 2, add 1 to them, and then multiply those together. That gets you 105 total factors. So using our strategy, we do 105 minus 24, which gets us 81 factors that are perfect squares. That aren't perfect squares. Okay. Does anyone have any questions on that? All right, for this one, how many of its factors are perfect cubes? So first step, as always, find prime factorization. And then for something to be a perfect cube, its exponent has to be either 0 or a multiple of 3. So again, we take the prime factorization and list those that meet the criteria. So 2 to the 0th, 2 to the 3rd, 2 to the 6th, those would make perfect cubes. Same for the other numbers there. And those are our total possibilities, so we multiply them to get 6 factors of 12,600 that are perfect cubes. Okay, so it's around the halfway point in this lesson. So So we're going to take a 5-minute break. All right, so return at 10:39. You guys can feel free to do whatever it is you need to do. All right, so let's continue. The next concept we're going to go on to is product of factors. So first, we're going to try to do this manually. So again, we're going to take 24, and I want you to try to find the product of the factors of 24. And you're allowed to use a calculator for this. Yeah, 331,776 is the correct answer. So basically you're just multiplying 1 times 2 times 4 times 6 times 8 times 12 times 24. So we're going to multiply together, and maybe you see a pattern. So you can see that each of the pairs of factors here multiplies to 24 itself. So 1 times 24, 2 times 12, 3 times 8, 4 times 6. And so doesn't that mean, since they're in pairs, we could have done 1/2 times the number of factors times the number? So let's try that out. So find the product of the number of factors of 25. You can go ahead and do this manually. Yeah, the answer would be 125. But if we try that equation we got before, we would have done like, we would have done 1/2 times the number of factors, which is 1.5, then times 25, which equals 37.5. And clearly that means our equation is wrong. It doesn't work for all numbers. So here are the factors of 25. And you can see why. It's because it's a perfect square, so it only has 3 factors. But there is a different equation that works. So we see that the only pair of factors that multiplies to 25 is the first and last one. So we have to multiply that by the square root of 25, or 5. And our equation becomes the square root of the number raised to the power of the number of factors. Does that work on 24? Well, if we find the square root of 24, and then we raise that to the power of 8. So it's the same thing as 24 to the 4th. And that equals our original answer. So that means this equation that's highlighted in yellow does work for all positive integers. Okay, so we're going to apply that equation to some example problems. Find the number of factors of 424. So first, that would be, we find the prime factorization to be 2 cubed times 53. And then we do our rule of adding 1 to them. So 4 times 2 equals 8 factors. And then now we find the square root of the number, and we use the equation. So we find the square root of the number, then raise that to the number of factors, which gets us the answer. So hopefully you guys all know how to use the square root function on your calculator. If you don't, feel free to ask. Okay, so now go ahead and try for 625. Find the number of factors and then use the equation to find the product of the factors. So we should take this one step at a time. So has anyone calculated the answer for the number of factors of 625 using our exponent plus 1 trick? What did you get for that? All right. So we find the prime factorization, and then our exponent, our only exponent is 4. So we plus 1 to that and get a total of 5 factors. Yeah, that's the correct answer. Good job. Then we find the square root of 625, and we raise that to the power of the number of factors. So nice job. All right, now onto some problems. Oops. Okay, you saw nothing. And you should attempt all of those, or as many as you can. So if you've solved number one, put your answer in the chat. Yeah, so all three of you got number one right. Nice job. And 27 factors for number two is also correct. So I'll give you some more time to work on 3 and 4 then. Okay, has anyone solved 3 yet? Remember, you don't have to actually like multiply it all out, but you can just write your answer as like a times. You can just write basically what numbers you would plug into the product of factors formula, because the number gets too big probably for your calculator to show all the way. And also you can put your answer for number 4, if or when you get it. All right, we'll do this for 2 more minutes. All right, sorry if we're still working, if you're still working, but we do have some other things we need to cover. So we're going to go ahead and look at the answers. You guys all got number 1 right, number 2 correct. And so Jivitesh, I'm pretty sure he probably put this in his calculator and it came out with like that really big number. When it says E, it's like too big to show. So you could have just written it as like the square root of 90 raised to the power of 27, which is 30 to the power of 27. And then for greatest common factor and least common multiple, you can find the prime factorizations. And then the only number that they all have in common is 2 squared. So that's 4. Greatest common factor is 4. And then least common multiple. So yesterday we learned the formula. Least common multiple times greatest common factor equals the product of all the factors. So that's the equation you see there. And then if you do a little bit algebra, then you know that the greatest common factor, that the product of all the numbers divided by the greatest common factor equals the least common multiple. So 21,504. Okay, so here are going to be some AMC problems. We might not get through all of them. That's all right. And these questions will cover content from both today and yesterday. So if you don't know how to solve a question, you can always private message me in the chat with whichever part is confusing you. So I know how to which parts to focus on when I'm explaining. First question, what is the largest 3-digit number that is a multiple of 12 and 21, but not a multiple of 22? So these problems are more challenging, but the best strategy for this is that it tells you it's a multiple of 12 and 21. So you should find the least common multiple of 12 and 21, which is 84. And now we're going to look for the largest 3-digit multiple of 84, which it happens to be 924. 924 is a multiple of 22, so we can't use that. And we find the next largest 3-digit multiple of 84, which would be 840. That is not a multiple of 22, so that fits our criteria. So basically, this is just like kind of trial and error. You start from the highest one and work your way down. If the product of two numbers is 360 and their greatest common factor is 9, what is their least common multiple? So quick hint, A times B equals GCF A B times LCM A. Okay, so using that formula, see if that helps you. Yeah, great job. So the least common multiple is 40, because you can see A times B equals 360 here, and you replace greatest common factor with 9. So basically, what times 9 equals 360? That'd be 40. Same explanation here. How many positive integer factors of 2020 have more than 3 factors? This one is pretty difficult, so I don't expect you guys to be able to do it, but let's just go through by step. So all of you, okay, so try finding the prime factorization for 2020 as your first step, and then put it in the chat. Yep, perfect. So that's the prime factorization. And then now, so we kind of have to think about what would make a factor have less than 3 factors. And so there are a couple of ways that would work. They could have like an exponent. They could have like just 1 factor, 2 factors, or like 3. So that's what their exponents could look like. And so for the first case, there's the 3 possibilities. You can see that their exponents are just like 1, 0, 0, 0, 1, 0, or 0, 0, 1. For our second case, we have only 1 possibility. And for our third case, we again only have 1 possibility because only 2 can be raised to the power of 2 here. So that is our answer. And then we just do our normal. Okay, so we find the we find the total number of factors, then we subtract the number of numbers with less than 3 factors, and then we get how many have more than 3 factors. This one, you can use that formula again. I'll write it out. Okay, so using this formula, we can solve this problem. Answer is 63. So that's the formula out there again. I'll get rid of mine. And then we just plug in the values that we know. So 63 times 7 equals a times b, or 3 squared times 7 squared equals a times b. Now, since both of them have a greatest common factor of 7, we know that they have 7 times 7. A and b both have 7 as a factor. Now, one of them has to have 3 squared as a factor, while the other has 3 to the 0th power as a factor. Because if they both have 3 as a factor, then the greatest common factor would be 21 and not 7. So the larger value is 7 times 3 squared, while the lesser value is 7 times 3 to the 0th power. And since we know a has to be the larger value, a equals 7 times 3 times 3, which is 63. Okay, so here's a simpler one. I think you guys should know how to solve this one. Just prime factorization and then apply the rule. So try your best. Yep, good. The answer is 42. So when you find the prime factorization, you get 2 to the 6 times 3 to the first times 11 squared. And add 1 to all the exponents, you get 42. All right, so we're going to skip past this problem and move on to the activity. So we're going to switch this up a little bit. We're not going to have 2 teams because there's not that many people in here. But what we're going to do is I'm going to give you access to these problems, and you can make a copy of it on your own. And then you have 10 minutes to solve as many as you can. All right. And then at the end, we'll see who has solved the most. These are a bit simpler than the AMC ones. Okay, so I'm going to put it in the chat. And then you guys should make a copy of it for yourself. Or you don't have to make a copy, but you can just show your, do your work on a separate piece of paper. And then once you're done, send all the answers as a private message to me. All right. I'll put up a 10-minute timer.
I won't have access. Could you represent your screen so I could do it on paper?
Okay. It might be because you
Thank
use
you.
a CPS account, but yeah, I can present my screen.
I'll try to add my account to this today or tomorrow.
Okay. We can set this in the backend and I'll switch to it every so often. All right, good luck. You guys have 3 minutes left. Okay, about 10 seconds left. All right, so that's the end. You can send your answers to me if you want. Send them all at once in one message, and I can tell you which ones you got wrong. Or which ones you got right. And we probably have time to like explain one of these problems. So if there's one in particular that you want me to go over, you can tell me right now. Otherwise, I'll probably just go do a short overview of how to solve them in the recording, but not like during this class, because I don't want to hold you guys over. Okay, so question 5. The positive integers x and y are the two smallest positive integers. Okay, so the product of 360 and x is a square. And from the lesson, we know that squares have to have all like even exponents in them. So 360, the prime factorization of that is 2 cubed times 3 squared times 5. So to make that into a perfect square, we have to, 3 is already fine because it's already has an even one. And then 2, we need to multiply by another 2 to make that get into 2 to the 4th, which is an even exponent. And then same for 5, we need to multiply a 5. So basically x equals 10. X equals 10. We found x. And now we need to find y. So for something to be a cube, its exponent has to be either 0 or a multiple of 3. So 2 to the 3rd is already fine. 3 squared, we have to multiply by another 3 to get that to be 3 cubed. And then 5, we have to multiply by 2 5s to get that to be 5 cubed. So basically we're multiplying 3 times 5 times 5, which is 75. So y is 75. And then the sum of x and y would be 10 plus 75, which is 85. So that's the answer for number 5. And that's the trickiest one on here. Okay, so let me just get to the rest of you sending messages in the chat. All right, so overall, it looks like you guys did pretty good, even with some challenge. And now, okay, on to homework. These are our homework problems, which will be posted in the classroom shortly after the lesson. So just do them. Oh wow, lots of big numbers. Okay. And we will review it on Thursday. Oh, right. And also no class tomorrow because that's Wednesday. But we will have class again on Thursday. Okay. So if you have any questions, feel free to ask. Otherwise, you're free to go. Bye, everyone. Okay. And a quick explanation of these other ones. So the number of factors of 7,560. Well, first you find the prime factorization, and then you apply the formula. So your answer for x should be 64 after doing that. And then y is the product of the factors of 36, which is also the square root of 36 multiplied by the number of factors of 36, which is 9, if you calculate it out. And so then you just do 6 to the 9th power divided by 64. And then your final answer should be 1,000, oh, sorry, this, I'll just write it up. 100777696, that's the final answer. The sum of the two smallest prime factors of 250, basically just find the prime factorization. And the two smallest prime factors are 2 and 5. So 2 plus 5 equals 7. Greatest common factor times least common multiple. So the greatest common factor of those two is 6. And then the least common multiple is 84. So just 6 times 84, which equals, it equals 504, I believe. And then the sum of the prime factors of 1,830. So you factor it out, and then you find the prime factorization to be 2 plus 5 plus 3 plus 3 plus 61 for a final answer of 71 for this problem. And then this one, as I explained in the lesson, should be 85. All right, so I'm just going to do this to hopefully make it a bit clearer which ones are the answers, because my handwriting on this is not that great. Yep, and that's that.